Today we would be continuing our journey with physics, and we would be starting electromagnetic waves, right? We already did ray optics, wave optics, optical instruments, all of that, even experimental skills. Okay, we discussed some experiments as well, right? So now we would be studying electromagnetic waves, and if time permits, we may move over to dual nature, because EM waves is not such a big topic actually for discussion. So let's start. You might have studied electromagnetic waves. Okay, and even though we were using electromagnetic nature of the wave or of the light, we were using a lot of it, but this is the first time we would be studying it, what it exactly it is. You know that actually when light passes through an obstacle, passes near an obstacle whose size is comparable to the wavelength of light, diffraction happens, and the reason for that is electromagnetic nature only. Okay, when this kind of thing happens, the electric field and magnetic field of light interact with electric and magnetic field of the obstacle, which causes this deviation. All the properties of reflection, diffraction, dispersion, they are all dependent on the electromagnetic nature. Okay, so it itself is a very diverse field, and when you reach college, you would be studying. Those of you who are actually into electronics and communication, all of those would be actually studying electromagnetic waves as a complete subject, and it is big, it is huge, right? It involves a lot of derivations. So here we would just have a small, very tiny glimpse of electromagnetic waves. The first topic we would start is displacement current. Okay, before we actually study electromagnetic wave, we would study displacement current. Okay, let us assume this arrangement. Let's say we have a capacitor with circular plates, right? And we have a battery, and let's say we have a switch here. Okay, initially the capacitor was uncharged, right? Initially the capacitor was uncharged, we assume that, and the switch was open. Let's say this is the EMF E, rather E. So let's say at t equal to 0, we connect this switch. What happens actually, as this switch is connected, current starts flowing and capacitor starts charging up, right? So you can see that, let's say I take an Amperian loop here. I'll draw it with a different color. Let's say I draw an Amperian loop here, right? Okay, Amperian loop over the wire, over the wire, okay, coaxial with the wire. Okay, the wire passes through the axis. So you can understand, as current is increasing, okay, for the Amperian loop, this, we can apply this closed loop integral B dot dl mu naught I. Since I is increasing, you can understand what would happen. Magnetic field would also be increasing. Since I is increasing, B vector would also be increasing. Okay, I'll draw another Amperian loop, let's say in between the capacitors, okay, and of same size. Okay, now this portion has no current between them, between it, the okay. Now this portion has no current flowing through it, right? So for the second loop, what? Mu naught I is 0, so, right, since there is no current, we can say B0, right? This is while charging. Once the capacitor is fully charged, the current in the wire also becomes 0, okay? Okay, so it is while charging, what happens, that current is flowing through the wire. So B here is non-zero and B here is 0. Now this is strange that the whole world is divided into two regions. One region which has magnetic field, this also has magnetic field, while the middle region has no magnetic field. Sudden discontinuity of magnetic field, it is impossible, right? The magnetic field cannot be suddenly discontinuous, so there is a discrepancy, okay, in the Ampere circuital law. So Maxwell worked on this. I'll just don't draw this right now. I'll elaborate on this. I'll draw the correct diagram. Okay, this is like a little simplified one. I'll draw the correct diagram for this, and then you can copy it. Okay. So Maxwell studied this thing. Maxwell argued that there is a term missing in the Ampere's circuital law. Okay. Okay. So let's discuss. Let's draw the correct diagram. So what he thought, what was the Maxwell's diagram was this. Okay. This is what? This is a hemispherical bowl. Okay. So what you have done? This is the capacitor plate. You have put a hemispherical bowl onto it. Okay. With a closed. Let us assume that the lid is also closed. A hemispherical bowl would have a closed hemisphere would have two possible surfaces. One is this flat surface, and other one is curved surface. Okay. Right. So what he said, Maxwell said, that actually, let's say for flat surface, if we apply Ampere's circuital law, we get magnetic field as non-zero. But if we apply the same law for curved surface, since no magnetic field lines are crossing the curved surface, right? No current is crossing the curved surface. Sorry, no current is crossing the curved surface. Magnetic field for the curved surface would be 0. Okay, just think about it. A hemisphere has rim. Okay, ऐसा होता ना circle. That hemisphere is like what? Your sabzi ka bowl, food bowl, right? So a food bowl has a rim. Okay, it has only one edge, that is its rim. Okay, the loop. So if it is closed, so even for the flat surface, the boundary is that rim itself. Even for the curved surface, the boundary is that rim. Correct? Okay. So for one surface, the flat surface, Ampere's circuital law for the boundary gives non-zero magnetic field. For other surface, the curved surface, it gives magnetic field 0 for the same loop. Now this is strange, right? He said this is strange. Okay. So it means Ampere missed something very important, which was this, that actually when the capacitor is charging, the electric field between the plates is increasing, or we can say the electric flux is also increasing, right? So which actually means that this electric flux contributes to some magnetic field production between the plates. Is it okay? Okay, so now you can draw the correct diagram, right? And you would write the important stuff. Somebody is saying no audio. Resolve हो गया या ना? Let's start. So now what he said, I'll draw. This is the loop C. Okay, let's say we have two surfaces. The flat surface is S1, the other surface, curved surface, is S2. So let the positive, yeah, let a loop C bound two surfaces S1 flat and S2 curved. Okay, so by Ampere's circuital law, for surface S1, closed loop integral B dot dl is equal to mu naught I, which means B is not equal to 0. Obviously, we can find the value of B, right? We can find the value of B by Ampere's circuital law for surface S2. So it would be means B is equal to 0. Okay. Okay. Now, I hope I can read the top line, right? I hope I can continue. So for same loop C, comma, the law gives different results. Okay. Okay. For different surfaces. Now this is impossible. So what Maxwell said, that actually Ampere missed a term called displacement current. So Maxwell suggested what? Displacement current. ID, which he said is epsilon naught d phi e by dt. Okay, which he said is d phi e by dt. Shall I raise? Now, so he modified the Ampere's law and called it Maxwell Ampere's law, which is this: closed loop integral B dot dl is equal to mu naught IC plus ID. IC is the normal conduction current which flows through the wire. ID is the displacement current. So I can replace it as mu naught I plus epsilon naught d phi e by dt. In this case, in fact, in every possible case, conduction current is always equal to displacement current. We can check this out. You know, the charge in the capacitor would be how much? CV. Rather, what? Charge तो ठीक है, okay. In fact, not charge, flux. Electric flux would be Q by epsilon naught. I can write it as Q is epsilon naught into phi E. Take di by dt, okay? Sorry, dq by dt, which is I, which would be epsilon naught d phi E by dt. Now this gives us the conduction current, the rate of flow of charge, while this gives us the displacement current. So they are equal, okay? So displacement current and conduction current are equal, but they don't coexist. Conduction current exists in wire and displacement current exists where electric field is changing. Is it okay? Where there is no conduction current. So either it's conduction current at a point or it's displacement current. So now you can see between the plates we need to include only ID, no conduction current, while on the wire we need to include only IC and not ID, right? Okay, so only one. In fact, it's like if IC is 0, ID is non-zero, or IC is non-zero, so ID is 0. दोनों एक साथ में, both of them can never be non-zero at the same time, right? At the same point. Okay. However, both of them can be 0. When the capacitor fully charges, what happens? IC, ID, both of them are 0, right? Yes? Never happens. Okay, shall I start? Now, so what he did now after this modification to the law, he said that actually there are 4 fundamental laws. He clubbed them together. Okay, 4 fundamental laws. Okay, on the basis of which whole of the electromagnetic phenomena can be explained. Okay, he called them Maxwell's equations. Okay, in which first one was what? Any idea? गॉस लॉ यही था शायद. गॉस लॉ इन इलेक्ट्रिसिटी, गॉस लॉ इन मैग्नेटिज्म, दिस मैक्सवेल एम्पियर्स लॉ एंड विच वन एल्स. वो तो मैक्सवेल एम्पियर सर्किटल लॉ तो हो गया ना. विच वन एल्स? I'll check the order. So first one was Gauss's law in electricity, which you already know is what? Flux through a closed surface, flux through a closed surface is 1 by epsilon naught times of the charge inside. Right. Second, Gauss law in magnetism. What is this? Any idea? Any idea? It would be pretty similar. What about this? Zero. Why? Monopoles don't exist. Okay? Monopoles don't exist. Okay? So, whenever you consider a surface, either you would have positive pole strength plus m, or you would have, if you have positive pole strength, you definitely have a negative pole strength in there as well, or you would not have any pole strength at all. Right? Okay? I repeat. Since monopoles don't exist, okay, so what happens? If you, let's say this is closed surface, let's say this is a magnet, okay, you are trying to apply Gauss law in magnetism here. Now you can say that if this is north, at this point a south would be there, a north, a south. Monopoles don't exist. So basically in this surface a north and south are there. So total magnetic charge or pole strength, whatever you may call it, from whatever terms you understand, total of that would be 0. This is plus m, this is minus m, right? Total would be 0. So the magnetic flux through a closed surface is always 0. Another way of thinking through this is that since if you consider a closed surface, since magnetic lines of force, magnetic field lines, they form a closed loop, right? Magnetic field lines form a closed loop. So what actually happens, that each one of the line would actually come out of the surface, then go in from somewhere else. Okay? So the amount of positive flux would always be equal to the amount of negative flux. Some lines would always leave and come back into the surface. So from that point also you can consider this, that the total flux through a closed surface, magnetic flux through a closed surface is always 0. Okay. Third is Faraday's law of electromagnetic induction. What happens in Faraday law? See, what happens actually, that Faraday law is the connecting link between what? Magnetic field and current, right? So it says that closed, what exactly does it say? ज़्यादा दिन तो नहीं हुए पढ़े हुए. What is Faraday's law of electromagnetism? Explain. Do you remember the statement? Online anyone? कोई बता सकता है? हाँ? ये क्या कह रही हो तुम? Whenever flux through a surface changes, there is an EMF is induced in it. ठीक है? वो तो lenses कहा था. And the induced EMF is directly proportional to rate of change of magnetic flux, electric flux nahi. So he said that induced EMF is minus d phi m by dt, rather d phi b, because we use b for magnetic field, right? D phi b by dt. This is EMF. I can write it as E dot dl. Can I write it as E dot dl? Integral of dot product of electric field with distance. याद है आप लोगों को? This was E dot dl with a negative sign. So actually there should be a negative sign here as well. कुछ ऐसा याद है? This was taught to you in electrostatics, right? ये form. The fourth one is Maxwell Ampere's circuital law. Okay, Maxwell Ampere circuital law, and this you already remember. इसका statement याद है? Let me ask. What is the statement of the Ampere circuital law? Maxwell वाला तो भूल जाओ. Ampere circuital law का statement क्या था? What was the statement? Huh? You are writing boards in 2 months? 3? Probably pre-boards would start in just 2 weeks. Huh? The line integral of magnetic field over a closed loop is equal to mu naught times the current in passing through the loop. Right? हैं? चलो अच्छा है, कुछ याद आ गया तुम्हें, हैं? प्री-बोर्ड से पहले. ठीक है? It was very difficult, right? I couldn't recall it. You helped me. Thank you. Shall I raise this? Okay. So one question for you. question is this. A parallel plate capacitor has radius 5 centimeter, has circular plates. Okay, a parallel plate capacitor has circular plates of radius 5 centimeter. Okay, it is being charged so that electric field increases at the rate of 10 raised to the 12 volt per meter per second. Okay, so find ID. करें? ID is epsilon naught d phi E by dt, which is actually d by dt of electric field into area. Area would remain constant, right? So this would be epsilon naught A dE by dt. Now dE by dt has already been given, so this would be 8.85 into 10 raised to the minus 12. Area would be pi r square, pi into 0.05 whole square into dE by dt is 10 raised to the 12. Right? You can find the answer. Okay, it would be approximately 0.07 amperes. Shall I start? करें? Somehow people don't find it very comfortable kind of chapter. right? But it's not that difficult. Okay, let's have another question, and let's see if you can pick this up. This one, the earlier one was pretty direct. A pure capacitor of C is equal to, just a second, just let me think the values. 100 by pi microfarad is connected across a source V is equal to 220 volt, comma 50 hertz. Is it okay? The plate area of capacitor is 0.1 meter square. Find ID. See, this would be actually, please remember this. This would be actually, you know, an AC source. Actually, I should mention. Frequency is mentioned already, so it's an AC source. Understood, right? So this one is an AC question. I would rather ask ID, rather RMS value of ID. Tell me one thing. 220, is that RMS or peak value? RMS. So whatever the current you find would be RMS. You asking me something? This was microfarad.
Okay.
Now check this out. This is an AC question actually. You need to find XC. You need to find the current, right? So XC would be 1 by omega C or 1 by 2 pi FC. 1 by 2 pi 50 C is 100 by pi into 10 raised to power minus 6, right? So this cancel, and this would be 100, this would be 100, so it get minus 2. It is actually 100 ohms, right? So the current, RMS current, the conduction current would be how much? E upon XC, which would be 2.2 ampere, and we already know that the conduction current is always equal to, बस इतना ही सोचना था. The question would try to mislead you into finding conduction current, but if you don't know that conduction and displacement currents are equal, you would always feel lost. पता नहीं क्या हुआ, right? There is. Last line. So this was the only, nahi, ek aur we have just one more derivation, but rest of all would be like theoretical concepts. You need to understand them really well. So what happens actually, let's say there is a capacitor, you apply AC, okay, you apply AC to capacitor plates. What actually happens? Let's discuss. Now what happens, let's say initially the charge on the capacitor plates was 0. This point gets positive polarity, this gets negative. So the capacitor starts charging, okay. Because of that there would be some electric field in this manner, this would become negative, right? And this increasing electric field behaves as what? As displacement current, produces a magnetic field like this, just like current. Current here is like this, okay. So the magnetic field lines are like this. So even for this displacement current region, they would be in the similar manner. I'll draw them. Even I would draw a bigger diagram. We would be doing a lot of stuff in this. Okay, so now the magnetic field lines, since the electric field lines are this, like this, so I can take the direction of displacement current as this ID, this is IC. Because of this ID, the magnetic field would be like this, okay, circular shaped. So right, this dotted portion indicates that this is behind the plane, while solid one indicates this is in front of the plane, right? So magnetic field would be like this, okay, and so on. Now since the electric field is, you know, it's the source is a sinusoidal thing, right? The charge would be in some form of sinusoid. The electric field would be in some form of sinusoid, okay, either sine or cos, plus phi naught I would write, so as to help you understand, okay. There would be some factor of, some phase factor as well involved, so we don't give a damn about the phase factor. It's like, what we need to understand here is that the electric field would be sinusoidal, and so the magnetic field would be some sinusoid, right? So they would all be sinusoids. So changing electric field produces changing magnetic field, right? Okay. And by Faraday's law, we studied that actually changing, we studied this form, E dot dl, for a closed loop. Let's consider a closed loop like this here. For a closed loop, it would be d phi b by dt. There was a negative here and negative here, they cancel out, right? Because this is minus
Okay, EMF is minus integral E dot dl, right? So from here you can get that that if magnetic field is a sinusoid, if magnetic field is sinusoidal, another electric field, induced electric field would be produced. Okay, I complete the picture now. So what happens, this is the sinusoidal source. Okay, the current flowing is sinusoid, the charge is sinusoidal, okay, sinusoidal form. Even the electric field is in the form of a sinusoid, which produces a magnetic field which is sinusoid, which further induces an electric field which is sinusoid, which further induces a magnetic field which is sinusoid. Getting it? So it's like a chain. It would continue. Anywhere we get a changing magnetic field, we would get a changing electric field, then a changing magnetic field, and so on. Anywhere we get a changing electric field, we would get a changing magnetic field, then changing electric field, and so on, right? So this combination of electric and magnetic field is always together, it comes together. This combination we call it as EM wave, electromagnetic wave. Okay, so electromagnetic waves are nothing but a combination of changing electric and magnetic field. Okay, obviously you would study in higher maths that any changing thing can be expressed as a combination of sinusoids of different frequencies. I don't remember the name, whether it was Taylor theorem or some other theorem, but you would study in higher maths that any changing thing, okay, any function can be expressed as a combination of different sinusoids of different frequencies. Any, except for constants, because they won't change, right? Okay, so here we had the starting point was a sinusoidal source. Here we had a sinusoidal source as a starting point, so definitely the electric magnetic field would have same frequency as the source, right? So EM waves produced would have the same frequency, right? So from here we can understand how electromagnetic waves are produced. Okay, you produce changing electric field, you get electromagnetic wave, you get changing magnetic field, you produce changing magnetic field, you get an electromagnetic wave, right? In every scenario you would get an electromagnetic wave easily. Now how to produce an electric field, changing electric field? Okay, a source, a charge at rest cannot produce a changing electric field. It's not a source of EM waves. A charge moving with constant velocity produces a constantly changing electric field whose derivative would become constant, right? Because you remember that B dot dl was mu naught epsilon naught d phi E by dt, right? I'm ignoring the conduction current because in middle space there is no conduction current at all, only displacement current. So you can understand this, okay? You can understand this. If a charge is moving at a constant speed, the electric field would change constantly, right? Would be, okay, uniform variation would be there. So if uniform change is there, okay, let's say electric field is increasing at a constant rate, so it is equal to, electric field is equal to E naught t. What happens in this kind of scenario? The derivative becomes constant. If derivative is constant, magnetic field is constant, it won't induce any electric field, right? So a charge moving with constant speed cannot produce EM waves, okay? Okay, through electric field mode it cannot, through magnetic field also it cannot, because a charge moving with constant speed is considered as a constant current. A constant current cannot produce changing magnetic field and electromagnetic wave. So the only way to produce it is using accelerated charges. That's what we were doing. Constantly the current was flowing like this, so the charges were accelerated. Is it okay? And that's why EM waves are produced. Since we are dealing only with sinusoidal EM waves, okay, I would be writing the sinusoidal equation. Should I raise this? It's not a very significant kind of thing. It's like you need to understand it here, Okay, okay, just make your own notes. So what happens? The electric field would be a sinusoid. I would write it as omega t minus kx. You remember that this was the wave equation in 11th class. This was the wave equation where x was the position of the point. Okay, okay, a wave is nothing but group SHM. Okay, okay, a wave is nothing but SHM of a group of particles. So you know it is actually equation of SHM, but there x is the position of the particle whose SHM you are studying. Since for different values of x you can study SHM of different particles, that's why you call it a wave equation. It is applicable to all the particles of the medium, right? So electric field, sinusoidal electric field is like this, while the sinusoidal magnetic field would be like this. Okay. Okay, shall I? So, you know, I won't be deriving these relation that E by B is C is actually V. B is V for any medium. Okay. Okay, for medium, and it would be C for vacuum. Okay. Okay, this is electric field at a point, this is magnetic field at a point at any time t. Okay, getting my point? E and B are electric and magnetic fields at any time t. Okay, this ratio remains constant even for maximum possible values. So we use this. Okay, we use this expression and the Faraday law and we find out that C is actually 1 by mu naught epsilon naught under root. Okay, I would be jumping over to just the formulas because the derivation is not even in the JEE syllabus. Okay, it would become really cumbersome if you study them. Right, and one more thing which is valid for any wave, the wave speed is given by omega by k. You remember how? याद है ये? नहीं. This is omega is 2 pi by t, where k is angular wave number, it is 2 pi by lambda. So if you solve it, it's lambda by t, distance traveled by time taken. Okay, so please remember this as well. This is valid for any type of wave. Right, shall I erase this? Now let's discuss energy density in EM wave. Okay, this can be derived easily. Right, the electric field in an EM wave is given by this thing. Okay, while the magnetic field is given by this thing. The density due to electric portion would be half epsilon E square while the density due to magnetic portion would be how much? Half mu naught, sorry, b square by 2 mu naught. Remember? ऐसा कुछ होता था? Energy density you already studied. This we found while we were studying solenoid. This we found for capacitors, and I said that it is valid for any electric field, not because of capacitors, but it is valid for any electric field anywhere in the world. This is valid for any magnetic field anywhere in the world. In fact, we went to this point, up to this point, that a solid sphere, a charged solid sphere has no energy. Let's say you have a not a solid, in fact consider hollow, it would be easier to understand. A hollow charged sphere has no electric field inside, it has no energy stored inside. Okay, it has all the charge on the surface. Okay, so the electric energy, the electrostatic energy of the sphere is not on the surface, it is in the region surrounding the surface, in the electric field itself. If you integrate the energy density, okay, add up energy density for all the space around the sphere, you would get the energy stored in the sphere. Okay, electrostatic energy stored due to charges on the sphere, right? So for charges, energy is always stored in the space between the charges, not on positive or on negative charge, never stored on the charges themselves, right? We studied this. Even for solenoid, we discussed this, that the energy is stored in the region itself. You remove the magnetic field, the energy is gone, right? So the total, I accidentally picked a red one. So the total energy density would be this, which would be half epsilon naught E naught square sine square omega t minus kx, while half b naught square sine square omega t minus kx by mu naught, right? This I just placed the value. Now the average energy density, you remember these angular brackets, they mean average. Okay, the average energy density, what is the average of this thing and the average of this thing? We studied averaging in AC. याद है कुछ? Half. Yes, somebody from here came up with the answer. Okay, the average for sine square omega t is half, while for sine it is 0. Okay, for half cycle it is how much? 2 by pi. For half cycle it is 2 by pi, right? Okay, so it would be 1 by 4 epsilon E naught square plus 1 by 4 B naught square by mu naught, right? Okay, okay. So this is the average. Okay, this is the average energy. Also, we can check one thing. We can check, the average energy density because of electric component would be this, right? But you remember that E naught is C B naught, right? E naught by B naught is C, right? I replace this and I get 1 by 4 E naught epsilon naught C square B naught square. Now C was 1 by root mu naught epsilon naught. C square would be 1 by 4 epsilon naught 1 by mu naught epsilon naught B naught square. So epsilon naught goes. This is same as the magnetic component, right? So from this all we proved that the energy density, the average energy density for electric is equal to average energy density for magnetic. If you know one, you can find the other. So the total energy, total average energy would be either 1 by 2 epsilon naught E naught square or 1 by 2 B naught square by mu naught, right? If you express it in completely magnetic format or electric format. Right? Can we continue? Okay, done. So now, question. So question is, for a wave, for an EM wave, the electric field, peak electric field is 120 volt per meter and the frequency is 50 megahertz, right? So you need to find E, expression for E and B. हुआ? The frequency is 50 into 10 raised to power 6. The wavelength would be how much? C by F. So this is 3 by 5, 30 by 5 rather, or 6 meter. Right? Okay? Okay, right? So the omega thing would be 2 pi F, which is 2 pi into 5, 50 into 10 raised to power 6, 100. So 100 pi into 10 raised to power 6, while the K would be 2 pi by lambda or pi by 3, right? Pi by 3. So the expression for electric field would be 120 sine 100 pi, or you can write it as 10 raised to power 8 pi t omega t minus kx pi by 3 into x. For B, this sign thing would remain same. The value of B naught would be different. B naught, since E naught by B naught is C, B naught would be E naught by C. You can find the value. I will directly write this is 120 by 3 into 10 raised to power 8 sine of the same thing. This is the expression for B. Okay. So for a very small amount of magnetic field, the magnetic energy is pretty large, right? It would be equal to electric component, energy of electric component, right? Shall I erase this? Okay. And hopefully I can consider this, that you would be able to find the energy density here. Is it okay? कोई issue तो नहीं होगा उसमें? I'll be erasing this. Now, shall I discuss the electromagnetic spectrum? It's a total game of memorizing. I won't be discussing it. It's not worth it. I would discuss the last thing, which is Hertz experiment. Okay. What is Hertz experiment? I'll draw the diagram. Okay. These are two metal plates. Metal plate A and another metal plate B. Okay. S1, S2, and this is the connection to induction coil. Done. So what actually happens, what induction coil was connected here. The role of induction coil is to produce high voltage, high frequency DC. Okay. Oh, sorry, AC. Yeah. So this produces high voltage, high frequency AC. Right. Okay. Because of this, what was happening because of repetitive, you can say this high frequency thing, high polarities of the two metal plates. What was happening actually was that these two spheres were getting, when Hertz performed this experiment, these two spheres were getting very high potential. One was getting very high positive potential, other was getting very high negative potential. Okay, and the gap between them was small. So basically, what happens? A spark jumps, okay, from negative to positive. Okay, so because of this sparking, what happens when spark jumps through an air gap? Charges jump through an air gap. It is highly accelerated thing. They start from rest, right? Okay, so they are highly accelerated, and in this arrangement, since they are highly accelerated, they produce EM waves, okay, of high frequency. Okay, now these two metal plates behaved as a capacitor. Okay, even though whole of the thing apparatus was between the plates, but they were behaving like capacitor. Okay, while this induction coil and these thick wires, they were behaving like inductors. Okay, so what was happening because of this arrangement? Okay, because of this arrangement, what was happening? EM waves of angular frequency 1 by root LC were getting produced. Okay, or frequency would be 1 by 2 pi root LC. Okay, a question was recently asked on this concept. Only on the formula itself. So as you can see that whenever there are inductor and capacitor in an arrangement and there is a possibility of sparking, EM waves are produced. Okay, so between the capacitor plates, that empty space produces EM waves, right? You know this. Okay, the space between capacitor plates produces EM waves. The frequency of those EM waves would be this. Is it okay? We did LC oscillations, right? AC में LC oscillations. The capacitor was fully charged. Okay, so the voltage here and here was equal. So it was like Q by C is the voltage here, and it is equal to minus L di by dt. Right? I can write I as dq by dt. So this would become d square q by dt is equal to minus q by LC. Right? LC oscillation was this only. Okay. So what was happening initially? The capacitor was charged and the switch was open, so inductor had no energy in itself. Okay, so when you connected, okay, what happened? The voltages became equal, and so the charge was satisfying, charge on the capacitor plates was satisfying this relation, and this is quite similar to d square x by dt square is equal to minus omega square x. Remember the equation of SHM? So omega in this case was 1 by root LC. Okay, same thing. Okay, so even in LC oscillations, even though there was no resistance in the wire, even then there was a loss of energy because the capacitor, the gap between capacitor plates was emitting EM waves because of accelerated charges, right? And the frequency was the same. It was the same as in this case. Okay, so this is behaving like the LC oscillation arrangement. Okay, the induction coil's role is to supply the lost energy. Okay, the role of induction coil is to replenish the lost energy, because the EM waves would actually waste a lot of energy, right? Actually, LC oscillations is had been pushed out of the uh, NCRT syllabus. It is in the NCRT, but out of CBSE syllabus. So that's why maybe it was not taught at that time. It was not written in the description, whatever is sent by Udan. Okay. Shall I raise this? I guess it's clear. Even LC oscillations is not difficult to handle. It's just these equations you need to understand, and the equations are pretty similar to SHM. Okay. So shall I raise this? One question. A light beam traveling in, acha, one more thing I would add before this question. The electric and magnetic components are perpendicular to each other. You know this, right? So this kind of arrangement can be drawn. If this is the electric component, the electric field is increasing like this, then decreasing. So the magnetic field would be something like this, perpendicular to this plane. Right? So now the question. A light beam is traveling in x direction okay, as given by EY is equal to 270 sine omega t minus x by c. Okay, another form of expressing out of omega t minus kx, take omega common. So one thing would be t, other would be k by c, k by omega, right, which is actually 1 by c. So this an electron moving in y direction at 2 into 10 to the power 7 meter per second speed enters the region of EM wave. Find maximum electric and magnetic force on the electron. the maximum electric field would be 270 into the electric force would be 270 into 1.6 into 10 to the minus 19 QE, while the maximum magnetic force would be QVB. We know V, we know Q. B you need to find. It is actually QVE by C. That's it. You can find it. It's easy. इतना टाइम लगाओगे कैसे काम चलेगा? Okay, so now intensity is the total energy crossing an area per unit time perpendicularly. Crossing one unit area, actually it should be. Okay, the total energy crossing unit area per unit time perpendicularly. Is it okay? So let's consider, let's say this is an area A on which EM waves are falling. Okay, total U energy is falling. Okay, let U energy be crossing or falling, whatever, on area A in delta T time. Right? Okay, in delta T time. Yeah, intensity is for light. So the intensity would be how much? Energy per unit area per unit time. It is also, if you combine them, energy by time, it is also power by area. Okay, right? And in 1 second light travels c distance. So actually in 1 second whole of the energy contained in this region would fall onto the plate. Is it okay? The area, right? So the energy density is how much? Half epsilon naught E naught square is the energy density into volume of this region. The volume of this region is A into C for 1 second, right? Upon A. So this is nothing but half epsilon naught E square into C, or the energy density in electric form, or the energy density, whatever you call it. Not in electric form, it is the total energy density. In electric form it was 1/4. So this is average energy density into C. Intensity is this. Okay, shall I raise this? Shall I raise this? हो गया? नहीं? अभी कर दूं रेज? Let's discuss momentum of light as well. Momentum, radiation force, or you can say light force due to EM waves. Okay, radiation force and radiation pressure. We would discuss all that. So momentum. Now, light is made up of photons. Each photon has energy. Let's call it this hc by lambda. While according to de Broglie, the wavelength is given by h by p, right? Can I say p is h by lambda, or p is e by c, right? Okay, okay. if n photons are falling on a surface in 1 second, if n photons are falling, then total momentum incident on surface कितना होगा? How much? NE by C, right? It's not difficult, so basic है. But this is in 1 second. This is momentum incident in 1 second. So I would call it momentum per unit time, right? This is force, right? So the radiation force is NE by C, which is the total energy incident on the surface. E is what? Energy incident on surface, right? I can also write it as IA by C. Why? Because intensity is energy by area, right? Intensity was energy by area per unit time. This is a per unit quantity, energy incident on the surface per unit time. Rather, I should be writing it as power. Actually, it is nothing but power. So force is actually power by C, which is IA by C. This is radiation force. You can understand what would be the pressure? What? Force upon area. The pressure due to EM waves would be F by A or I by C. Okay, please write this down. I would add something more, some little bit more, and then we would do one question. Shall I erase this? At least the top few lines. Right? So now, if light is absorbed on this surface, the change in momentum would be how much? Only IA by C. The momentum is absorbed, right? Final momentum is 0. Momentum of the photon finally is 0. Initially it was IA by C, right? The force would be IA by C, right? The pressure I by C. You can find it out. But if there is reflection, what happens in reflection? Nahi. The change in momentum is twice. Direction change. Right? Because of direction change? Kya? Huh? Yeah. Final momentum would be in the opposite direction. So the change in momentum would be twice IA by C. So force would be twice IA by C, while pressure would also be double. Right? And you know, all the spacecrafts which are sent out of Earth's area, gravitational range, actually operate on this thing, right? What happens actually? They have very large sails of very thin, light material. Okay. So what happens when they go out of Earth's atmosphere? Okay. Some satellites, some spaceships which are sent to, let's say, Neptune or Pluto or to explore outer world. For those actually, what happens? when they reach, when they go beyond Earth's gravitational pull, they actually open their solar sails, and because of because of the radiation energy of the sun, radiation pressure, radiation force, they keep on accelerating. Okay, and recently there was a satellite named Cassini. Its question appeared in Kaun Banega Crorepati. Okay, so there was a satellite named Cassini, and it deployed this thing, this solar sails kind of thing, and right now it's passing nearby Neptune, or even crossed that range, and right now it is moving at 40,000 kilometer per second speed because of this force, solar force, radiation force, right? So let's have a question. One question, you need to identify the concept as well. The question is, a red LED emits fact of power 0.1 watt, emits light uniformly in a spherical space. Okay, find amplitude of electric field at 1 meter distance from LED. Okay. Okay. So power is given, right? When the distance is 1 meter, you can find the area in which the same power has dispersed, right? Just go on, do it quickly. नहीं हुआ? How much would be the intensity? This is the LED, okay, and the light produced by it has spread into 1 meter space, right? Equator into a space of 1 meter radius, spherical space is written. So this 0.1 watt power is distributed into this whole of this area. So the intensity would be power upon area, which is 0.1 upon area is 4 pi 1 square, 4 pi r square. Okay, you can find the value. Okay, but if you remember, how much was the intensity? It was half epsilon naught E naught square C. This is what was asked. Okay, so E naught would be how much? 0.2 upon 4 pi epsilon naught C under root of this. 1 by 4 pi epsilon naught is actually 9 into 10 raised to 9. Okay, so this is 0.2 upon into 9 into 10 raised to 9. This is 1 by 4 pi epsilon naught. Okay, C is 3 into 10 raised to 8.
So this is 3, 1 goes, this is 6 actually, root 6. The electric field would be 2 point, how much? 2.45 volt per meter. Right? This was a direct question asked in JEE Mains 2015. Okay? JEE Mains 2015, yes. Okay? So that's all. And we have finished this chapter. We would be continuing with modern physics, which is dual nature, then atoms, nuclei in the next class. Thank you.